Okay, so today we're going to sort of pick up where we left off with yesterday at this example. Just to give you a reminder of what we were doing, we had talked about qualitative and quantitative data and summarizing that data and looking at a sample. And what we wanted to do was use a sample as an estimate for a population. Okay. And so we talked about how we can summarize the sample by counting up the number of yeses in some particular question and then summarize that as a percentage. And we could also do that with the population. Even though we're not going to with the population, what we want to think about is that our summaries statistics, right, like that proportion for the sample is a good estimate for the population, right? And that's what we want to start delving into a little bit more. Okay, so in this example, I think we'll maybe dive a little bit further and start to make some of this process a little more clear. So what we're going to do is we're going to use a simulator to repeatedly collect samples of 100 peanut M&Ms. Okay, and let me see if I can get. Let's see if I can get a simulator going here. Okay, so this is a simulator for doing the same sort of thing. This is Reese's Pieces instead of M&Ms, but we have the same idea. So what I want to do real quickly is sort of go through what it is that we're doing. What is our simulator going to be doing? Okay, and what we want to do is, instead of just thinking about collecting a sample and getting data from that, what we're going to do is think about, what if I collect samples over and over again? What happens there? Okay, and this isn't something that we would do in practice. What we want to do is collect a bunch of samples over and over again so that we can see how samples in general behave, so that when we have one sample, we know what sort of conclusions that we can draw about it. Okay, so what we're going to do is we're going to repeatedly collect samples of size 1,000. So it's like collecting 1,000 M&Ms, or in our simulator, it'll be 1,000 Reese's. Okay, and if you remember back to our earlier example, our goal was to take 1,000 M&Ms and we could record the weight for each, and then we could record whether or not each one was green. Okay, and I think in my simulator it's going to be Reese's, and it's recording whether or not they're orange, but we'll do the same idea. Okay. Okay, so we're going to take 1,000 candies in our sample, and what I want to do is I guess this would take all day to sort of fill up the 1,000. See if we can hide the candy machine. Okay. But what it does is it's going to put a dot here on the number of orange candies that we had. Okay. This looks like it was, somewhere like maybe 208. And what I can do is I can take another sample, and this just is simulating taking a sample of 1,000 candies and counting how many are orange. Okay. Yeah, there we go. Show previous. Here, let's reset it. Okay. Okay, they're there. So as I take samples, you can see every time I click, it's supposed to draw another sample. Why is it? It's waiting for the candy machine. Oh, undo the animate. Nope, still didn't work. All right, well, this isn't working the way it's supposed to. I have to keep hiding and unhiding this candy machine to get the dots to show. But what's happening is every time I take a sample, it's going to put a dot for how many orange uh, candies I have. And I can change that to a proportion instead. But maybe number is easier to read. I don't know. Okay. And instead of taking one at a time, let's take a bunch of samples, right? The idea here was to do this over and over again. So in our example here in the notes, we've taken 16,000 samples of 1,000 each. Okay, so it's a lot of candies that we're counting. Okay, but again, we're just simulating it. So what I'm going to do is I'm going to take these samples 100 at a time. Okay, and it fills in 100 dots for me. Okay, with the number of orange candies. And it's just kind of spread all over the place, right? But as I take more and more, right, as I get here, this is over 1,000 samples, you can see that it clumps up in the middle. And there are fewer that are very high and very low. Okay. So now I'll add 2,000 more samples, and you can see that this process is getting, much more clear. There's a lot of dots on the screen. Okay. It's starting to fill in the gaps, and it's starting to take on that bell-shaped curve that we have talked about as being so characteristic of a normal distribution. Okay. Okay. So now we look at what does it look like when I have 33,000 samples. Okay. And now most of the variations from a nice normal curve have kind of been smoothed out. And you can see that we have this pattern here where it starts to look like a normal distribution. Okay. And what we want to do is take advantage of that. What that means is that if I looked at lots and lots of possible samples, they form a normal distribution. Okay, so when I take one sample, I can think of it as somehow being connected to a normal distribution. And that's what we're going to take advantage of. Okay, so when we take lots of different samples, we can make a few notes. All right, so the shape of the histogram appears bell-shaped. Okay, if I look at this one here, it looks like my tall middle center here is right around 0.15. So that's also the mode, and it's symmetric about that point, right on either side. Okay. If we were to look much more closely, remember when we talked about a normal curve, we could talk about where it switches from bending up to bending down. And if we were very careful about it, we could measure where that point was, right? So maybe that's like 0.14. And on the other side, maybe it's like 0.16. But I don't have a very carefully measured graph here, so those are just very approximate. Okay. But on a normal curve, that tells me the standard deviation, the distance from the middle to that inflection point where it changes is the standard deviation. So I can look at this and I can start to get an idea that maybe this can, looks like can be approximated by a normal curve where the mean is 0.15 and the standard deviation is 0.01. Okay. And in actuality, right, we have our summary statistics. The standard deviation was actually 0.0112. Okay. So what happens is even if my data is non-numeric, it can't possibly be normally distributed if all I have is like yeses and nos. But if I look at the percentage of my sample that responded yes, or in this case is green M&Ms, then all of those percentages themselves create a normal distribution. And that's what we take advantage of. Okay, so it's a little bit convoluted because we have more than one thing here going on, right? We take an M&M and we look at whether or not it's green, yes or no. And I do that for a whole sample. And when I look at the percentage of that sample that's green, maybe it's 17%, maybe it's 12%, whatever it is, okay, that gives me something to look at. If I imagine repeating that process, looking at lots and lots of samples, I now have numbers to work with, and that's what forms the normal distribution. Okay, so we're working with non-numeric data, which is just yeses and nos, but by looking at the percentage of yeses, that gives us numeric data to work with. Okay, and it gives us some formulas that we can compute. Okay, so if you take a random sample of size n from a population with a population proportion p, then the distribution of p hat has a mean of p and a standard deviation that follows this, formula here, right? The square root and stuff going on. Okay. Don't worry about those formulas. You're not going to be required to, plug them in manually. I'm going to show you how you can get your calculator. It has these formulas built in. I'll show you how to get your calculator to do the computations so that you don't have to get confused over stuff. Okay. One of the things to note is that the standard deviation of our random variable gets smaller as n gets larger. If I look at this formula, the n is in the denominator. If you divide by bigger and bigger numbers, your number will get smaller. And this thing here is the standard deviation. So I can see by the formula that as my sample size gets larger, standard deviation gets smaller. And remember, that's measuring the variability, right? So smaller standard deviation is more consistent data. So if we have a bigger sample size, we'll have more consistent data. What the data is that we're talking about are the samples themselves. The samples are going to be more consistent or more reliable when the sample size is larger. Now, that's something that we should hopefully know intuitively, but here's a way that we can see that mathematically, that we can see, yeah, bigger samples give us a better chance of that sample being a good representation of the population. Okay, and then we have these two conditions. The distribution of p is approximately normal if we have these two things, okay? And it's kind of like three things because this first one is a double. Okay, so let me explain what these are. So first of all, this first condition is really just checking to make sure that our sample size is large enough. Okay, now it would be really nice if saying the sample size is large enough, if we could just say, like, give me a number, like, is 30 big enough? Okay, if it's bigger than 30, that should do it, and we're good. Unfortunately, it doesn't really work that way. And let me see if I can show you why. See if we can use the simulator here. Okay, let's suppose that I take a sample of size, we'll say 50, but the probability of getting an orange Reese's is really, really small. Okay. Oops, I'm doing two samples at a time. All right. That's all right. When I draw my samples, they're at 0. I draw some more, they're at 0. I keep drawing samples, I get 0. Every once in a while, I might get one with 1. Okay. But for the most part, I'm getting a bunch of zeros. Okay. And if let's reset this. Let's make the probability even smaller. Okay. So here, now, I'm always just getting 0. I'm never finding an orange Reese's. Okay, when I take a sample size of 50, That's just not enough. The probability of getting an orange Reese's is really small. So I can't really tell if there even are any orange Reese's. Okay. If I take a sample size that is much larger, just go ridiculously large, 5,000 here. Okay. Now I get some ones. And some ones and zeros, right? So I can start to see that there are, different possible numbers that I can get. Okay. 0 and 1 and so on. All right. A larger sample size is enough to distinguish the difference between there being none and there being, very few. Well, 1 in 5,000 is pretty few. Okay. But I still get some different data when I take different samples. When I have a really small sample, if the probability of orange is very small or very large, I don't get that. So what happens is we need a formula that not only takes into account how many things we have in our sample, it also takes into account whether or not we have one of these extreme probabilities. Is the thing we're looking at, the yeses, really rare or really common? And that's what this does. It checks to see that our sample size is large enough, taking into account that we might have rare probabilities. Okay. The next condition is checking to see that our population is large enough. Okay, that's something that we might not have thought about as being that important, but and the reason why we need a large population is a little bit more subtle. Okay, but I'm going to give you a quick example to maybe illustrate why we need to do this. When we take samples, especially if we're taking samples of people, we don't ever think about sampling the same person twice, right? So for example, if I wanted to interview 20 stats students to see whether or not, they find the class difficult, I wouldn't sample the same person 5 times and then 15 other people. I would sample 20 different people, right? That's all, studies everywhere. That's what we do. Okay. Let's imagine a smaller scenario. Let's suppose that let's go back to candies. Let's suppose that my population is a bag of 10 candies, okay? And I want to take a sample out of there, okay? Maybe I want to take a sample of size 3, okay? And let's suppose the candies have different colors, like, we'll say red, blue, and yellow, okay? If there are 5 blue candies in the bag, when I take my first candy, I have a 50-50 shot of drawing a blue candy, okay? But if I do take out a blue candy as my first one, then when I go back to take a second one out of the bag, now there's only 4 blue candies out of 9 candies. That's less than a 50-50 chance. So the probability has changed now of me getting a blue candy. All right. So when you have a very small population, the probabilities change as you're drawing your sample. If the population was very large, if I had a billion blue candies, or a bag of a billion candies, okay, and I draw one blue one out, that's not enough to change anything. So just like with people, right, if I'm looking at a large population, like all the people in the US, and I take a sample of size 1,000, it doesn't really matter, when I take one person out of the population, when I go to draw my next person, it's still like almost the exact same probabilities. But if my population were very small, I'd run into a problem. Okay, so here's why we have these two checks. We need to make sure our sample size is big enough and that our population is big enough. Okay. Most of the time in real life, we don't actually know the size of the population, right? If I told you that we wanted to sample people in Illinois and, ask them a question like, do you think the governor's doing a good job? You don't necessarily know how many people are in Illinois, but you know that it's a large number, right? It's in the millions, right? So oftentimes we don't know the population size, but that's okay. We have enough context to know that it's really large. Okay, that's the sort of background stuff. Let's look at, let's sort of dive into some of the nitty gritty. Okay. What we want to do is not look at taking millions and millions of samples. What we really want to do is look at what happens when I take one sample. Okay, so we're going to define some terms, and then we're going to look at taking one sample, and then we're going to look at what that sample can tell us. All right, so let's define a couple terms. The first term, a point estimate. A point estimate is a single number. I think I'm going to type this out. Okay, a point estimate is a single number computed from sample data used to estimate a parameter. Okay. All right. This looks like a very complicated definition. To explain it kind of simply, examples of point estimates would just be like the average. Okay. So the mean is a point estimate. Okay. So if I'm looking at a sample and I compute the average, that's a point, okay, that gives me one piece of data. All right. What makes it an estimate is that I'm using that information from the sample to estimate the population. Okay. So when I say the mean is a point estimate, what I'm saying is if I look at a sample, let's suppose we take, the 30 people in our class, and we say, okay, I want to look at how long you spend doing your homework. Okay, I can get an average for our class. If I then say, all right, I think that the average for all 101 students is that amount of time, okay, then that's using that average as a point estimate for everybody. Okay, so the mean is a point estimate, okay, when it's used as an estimate, right? Okay. All right. So the two types of point estimate that that we can talk about, if I have numeric data, I'm going to use X bar, which remember is the sample mean. As a point estimate for mu, which is the population mean. Okay. We're not actually going to do examples like that, though. What we're going to do is examples where we use p hat, right, which is the percentage of yeses in our sample. Okay. And remember that the p hat one is for the sample, and the p one is for the population. But both of these are the percentage of yeses. Okay, it's just of those two different groups. Okay. All right. What I want to do now is introduce the idea of an interval estimate. Okay, so if I take a larger sample, that will give us a better point estimate, right? We talked about that. As your sample size goes up, this variability among samples decreases. So each sample is going to be closer to the percentage that you get in the population. Okay, but they still don't match exactly. Okay, so even if I take a large sample size, I know that in the sample they won't match exactly. So instead of looking at a single number, we can also look at a range of values, an interval of plausible values. Okay, and that gives me an interval estimate. Okay, so an interval estimate, and this is also going to be referred to as a confidence interval. Okay, and actually I think we'll probably mostly refer to it as a confidence interval. Okay, but strictly speaking, a confidence interval is just one type of interval estimate, but for our purposes, we'll use them interchangeably. Okay, so this is an interval of numbers around the point estimate that we will have a certain level of confidence that it contains the true value of the population parameter. Okay, so here's a little line graph that illustrates what we're talking about. I have a point estimate in the middle. Okay, maybe my point estimate, I opened a bag of Reese's, okay, and our bag of Reese's had 15.6%. I'm sorry, we took M&Ms. 15.6% green M&Ms. Okay, so we could say that our point estimate is that there is there are 15.6% of the M&Ms are green. Okay. Instead of having just a point estimate, we might also be able to construct an interval estimate. Okay. Let me just grab some numbers here real quickly. Okay. So I might have an interval where I say, okay, maybe between 13.3% and 17.8%. Okay, of my M&Ms are green. Okay. What I'm doing here is I'm giving you a range of values, right? I don't know exactly how many green M&Ms there exist in the world, right? But if I look at my bag of M&Ms and I see that there's 15.6, I think that it's probably close to 15.6, but I recognize that might not be exactly right. So we create this interval. We say, okay, I think it's somewhere in this range of values. Okay, and we're not creating this out of nowhere. What we're doing is we're leveraging that normal distribution from before. Okay, and in real life, you probably never hear people talk about an interval estimate. Well, you do. It's just disguised. Okay, so if if it's election season and I'm listening to a poll and they say this candidate has 60% of the vote, or this elected official has a 42% approval rating, something like that. Somewhere buried in the screen, they'll probably say with a margin of error of 4%. That margin of error is telling you what the interval estimate is. Okay, so if I'm looking at M&Ms, I would say in this case that there's 15.6% of all M&Ms are green, even though I didn't look at all M&Ms. And then what I could do is I could say, well, to get from my point out to the edge of my interval estimate, I have to go a certain distance, right? If I take that 17.8 and I subtract 15.6, I get 2.2%. So I would say that I have a 2.2% margin of error. Okay, and it should be the same on both sides, although my 13.3 doesn't exactly look like a 2.2% because of rounding error. Okay, one of these numbers rounded and the other one didn't. But it should be about the same on both sides. Okay. So I have the same 2.2% on both sides. It's symmetric. Okay. So let's look at this in more detail, because these confidence intervals are confusing. So I want to be very careful about what we're saying. So the idea is, if I could look at every single sample that we could take from the population, right? So if I'm taking bags of peanut M&Ms and I'm looking at 1,000 of them at a time, if I imagine every possible sample of 1,000 M&Ms that I could take in the world, okay, I could find the percentage of green M&Ms for each one of those, okay? And for each one of those, I'll get a slightly different point estimate, okay? And I can create this confidence interval. All right. If I'm creating a 95% confidence interval, we'll just use this as an example. And in the notes here, we say C%, okay? But if I just throw a number in here, if we say, all right, I want to create these 95% confidence intervals, what that means is that 95% of every possible sample that I can come up with will create a confidence interval that actually contains the real percentage of green M&Ms. And 5% of those intervals would not. Okay. So if we look at every possible sample of 1,000 M&Ms, okay, and create 95% confidence intervals for each one, then 95% of those samples give a confidence interval that contains the real percentage of green M&Ms. Okay. Now, we don't actually get to take every possible sample of size 1,000. That's not really possible to do. What we do is we take one of them. But if we think about the process, if I say, well, 95% of all of the possible samples that I can pick will give me a confidence interval that will give me, that contains that true value, then I could say I'm 95% confident that one single sample gives me a confidence interval that contains the true percentage. Okay. That means that there's still that chance that we picked one of those bad samples that doesn't give us that. Okay. And you might be aware of this with like political polling, right? You take a poll of people and you get a percentage, and sometimes that's wrong. And it's not that statistics isn't working. Built into statistics is, hey, sometimes your sample isn't representative of the population. Now, there are other problems with polling, right, that have to do with, is my sample truly random, right? Is everyone in the population equally likely to be chosen? Some people don't respond to polls, right? Some people don't pick up their phones. Some people are working. Other people are home all day and are very happy to respond to polls. And it turns out that if you respond to one poll, you get called for a lot of other polls. So it's not really random, okay? But we'll talk about that more later. The point is that even when we do everything right, our sample might not be a good representation of the population. It might be, far enough away or unique enough, right? The particular bag that we pick. Right? If you imagine all the M&Ms in the world in a giant bowl, and I take a scoop out of that bowl, even if only 15% of all M&Ms are green, it's possible that when I take a scoop out of that bowl, every M&M in my bowl is green. It would be really rare, but it's possible. Then that bowl would not be a good representation of what all the M&Ms look like. Okay, so there's always a possibility that your sample isn't a good representation of the population, even when you do everything right. And we account for that in statistics. So that's why we never say we're 100% confident. If we create a 95% confidence interval, then we're only 95% confident that everything we did is right. And that's separate from this whole margin of error business. The margin of error is just telling us how wide that interval estimate is. Okay, so let's look at another example to hopefully make some of this a little bit more concrete and clear. Okay, let's suppose that I have a 95% confidence interval for the mean or average age a woman gets married in 2013, and that confidence interval is 26 to 28. Okay, so what I want to do is look at what does that mean. Okay, so I'm not computing the confidence interval. I'm given the confidence interval. I just want to say what does it mean when I have one. Okay, so we can be 95% confident that the average age or mean age a woman gets married in 2013 is between 26 and 28 years old. Fix this so we can read the whole thing. Okay. So what we're doing is we're saying that we're pretty confident that the actual average age is between 26 and 28. Okay, let's look at another example. Suppose a 99% confidence interval for the proportion of Americans who have had tried marijuana as of 2013 is, and it gives us our interval here, 0.35 to 0.41. State the statistical interpretation of this statement. Okay, so I want to say, what does this mean? I'm interpreting what this confidence interval means again. Okay, so we can be 99% confident that the percentage of all Americans who have tried marijuana as of 2013 is between, and instead of writing these as decimals, 0.35 as a percentage is 35%. Okay, so when we're working with percentage, or working with proportions, it's usually more friendly looking to write them as percents. So I could say is between 35% and 41%. Okay, so what we're doing is we're saying, based on the sample that we took, we recognize that we don't know exactly how many people in America have tried marijuana. But based on our sample, we're very confident that it's between 35% and 41%. Okay. Before we start computing these, let's look at one more thing. When we look at a confidence interval, right, I could have a 95% confidence interval, I could have a 99% confidence interval, and you might ask yourself, why wouldn't I just use 100% confidence interval every time? Seems like an easy fix. All right, let's look at what happens when I take a higher level of confidence. Okay, suppose I'm looking at the exact same data, right? I took a sample and I'm just going to analyze it mathematically. If I take a 90% confidence interval, right, I get some range of values. To be more confident, I need a bigger range of values. Okay. An analogy I like to use for describing this is, let's suppose you're throwing darts at a dartboard, okay, and you're just yourself throwing darts with whatever skill level you have, okay. There's a chance that you hit the bullseye, okay. If you want to be more confident of hitting the bullseye without improving your game, right, if you just want to be more confident, you need a bigger bullseye, right, you need a bigger target to hit, okay. So if you had a really big target, if your target was the whole wall, you can be very, very confident that you're going to hit it. Okay. If you have that tiny little bullseye from 20 feet away, then you're not very confident you're going to hit it. Okay, or at least less confident. I'm not trying to judge your dart skills here, but the bigger your target, the more confident you can be that you'll hit it. So that's that idea here. A bigger confidence level goes hand in hand with a bigger confidence, a wider interval. And if I want to be 100% confident, then the interval is going to be so big that it would go from 0 to 100%, which tells you nothing, right? If I say I polled people and I am 100% confident that between 0 and 100% of people approve of the job the governor's doing. Well, you don't need a poll to tell you that. It's always between 0 and 100%, right? So it's 100% confidence is just not going to be helpful because it makes our interval infinitely big, right? Okay. So that's a trade-off. If I want to be more confident, then what I get to say is a little bit less precise. If I want to be very precise, if I want that small margin of error, if instead of saying that the percentage of people who smoke marijuana, if I want to say that that's, instead of saying between 35 and 41%, if I, if I want to say it's like, between 37.5% and 38.5%, right? That real narrow range, or it's about 38%, okay? Then I would have to be much less confident of my interval. I'd say I'm only like 60% confident that it's in that range. Okay. If I have a larger sample, though, that always helps. A larger sample always makes my interval smaller, so I can be more precise. Okay. And of course, the largest possible sample is if you just look at the whole population, then you're perfectly accurate. Okay. But in general, larger samples give us a better idea. So here's a little graph to show you. If I have a small sample size, I get this big interval. If I were to have taken a larger sample, I would have a smaller confidence interval, or you could say a smaller margin of error. Okay, and sample size 1,000, it gets even smaller. Okay. One of the things that I really want to emphasize, though, is remember that how wide the confidence interval is. Okay, that's what the margin of error is telling me. Okay, so this margin of error is this width. That's different than that percentage that we're talking about. So whether we say 90% or 99%, that's not the margin of error. The margin of error tells us how wide the interval is, or what that range of values is going to be. Okay, so let's outline the process we're going to do, and then we'll look at an example. Okay, so I'm going to come back and refer back to this because I think reading through this is kind of a lot to take in. So actually, I think what I'm going to do is I'm going to get started in our example, and then I'll come back and refer to this as we go. Okay, so that we can see what all of this stuff means. Okay, so here's our example. A researcher is studying the effects of income levels on breastfeeding of infants and hypothesizes that countries where the income level is lower have a higher rate of infant breastfeeding than in higher income countries. Okay. It is known that in Germany, which is considered a high income country by the World Bank, 22% of all babies breastfeed. And in Tajikistan, which is considered a low income country by the World Bank, researchers found in a random sample of 500 new mothers that 125 were breastfeeding their infants. Okay. Now notice that they didn't tell us a percent, right? Here we have a sample and here we have a percentage. So we'll deal with that in a minute. Find a 90% confidence interval of the proportion of all mothers in Tajikistan who breastfeed their infants. Okay, so there's a lot to this. We want to be very careful about our process. Okay, so what I'm going to do is I'm going to start by stating my random variable and what my parameter is so that I know what it is I'm looking for. If I try to just jump in with the numbers, I'm going to confuse numbers. And when I get a number at the end, I might not know what that number is. Okay, there's a lot going on, so I want to be careful and deliberate about this. So we're going to start by labeling what our random variable is, the p hat, what it means in this context, and what our parameter p is. Okay. So here, my random variable p hat, okay, is the percentage of mothers in Tajikistan that breastfeed. And when I say percentage, it's the p hat is the percentage of my sample of 500. So this is the percentage of the 500 mothers that we sampled. Okay. The parameter p is the percentage of all mothers in Tajikistan that breastfeed. Okay. And one of the things I want you to notice is when we're going through this, there's typically like a question that we're trying to answer. Okay. What we want to know is what is the proportion of all mothers in Tajikistan that breastfeed? Okay. That's what our parameter P is, right? That's the thing of interest. So we're not really interested in what percentage of our sample breastfeed. What we're interested in is what percentage of all mothers in that country breastfeed. Okay, so that we can test this hypothesis that this researcher has. So that's a thing to keep in mind. The parameter is looking at everyone in the population, which is the question we're really interested in. Okay, that random variable p hat is looking at the percentage in the sample, which is the data that we actually have. Okay, let's go back to our reference to look at what the next step is. We want to state and check the assumptions. So here what we need to do is make sure that our sample size is big enough by using this formula, and make sure that our population is big enough. Okay. All right. So in our acronym part, this is the P portion. Okay. So now let's look at the A portion, which is the assumptions. Okay. So I need to check that. Well, let's look at it. We sort of had two different ways that we could do this. We could say n p hat is bigger than 10 and n times 1 minus p hat is bigger than 10. Okay. It says in here this is the same as x is bigger than 10 and n minus x is bigger than 10. This x is how many people said yes. And this n minus x is the number of no's in our sample. Okay. So if I come down here to our example, in our sample, so let's make sure we're focusing on our sample. In our random sample of 500 new mothers, 125 were breastfeeding their infants. Okay, so I need to check that x is bigger than 10 and n minus x is bigger than 10. So x is just the number of people that said yes, or the number of breastfeeding mothers, right? So here, x is 125, and our sample is 500. And remember, n was the sample, the letter that we used for sample size. So n is 500. So here I can see, oh yeah, x is bigger than 10. So x is 125. That's bigger than 10. Put a check mark there. Okay. And n minus x, 500 minus 25, is the number of no's. It's 375 mothers said no, they don't breastfeed. That's also bigger than 10. Okay. Now we need to know about the population size. Okay. Does anyone know the population of Tajikistan? You could look it up and get an approximate number. Okay. But we don't have an actual number. And looking it up and getting an approximate number would probably be a good thing. But the thing is, I know that it's going to be really, really big. What we need is we need that n is bigger than 20 times little n. Okay. My little n here is 500. Okay. If I take 500 times 20, that's 10,000. I don't need to go look up the population of Tajikistan to know there's more than 10,000 people that live there, right? I mean, it's a whole country. Okay, it's not a very big country, but it is a whole country. So we need some light blue. So we also need to check that capital N is bigger than 20 times little n, which is 20 times 500, which is 10,000. Okay, so what we do is we say our population size, big N, is unknown, but larger than 10,000. Okay, so we say, all right, we get a check there. So now we've checked our assumptions that the sampling, or that our sampling distribution of p hat is approximately normal. Okay, now what we're going to do is we're going to use our calculator. Okay, and in particular, I want to use this 1 proportion z interval on my calculator. Okay. All right, so my next step here I'm going to use the 1 proportion z interval. Okay. And come up with my interval estimate. Okay. So here in our procedure, it sort of walks you through and gives you some pictures of what this looks like. So I'm just going to show you here. Okay. Well, so let's just look at it as we go. Okay, so here's my calculator. In order to use this 1 proportion z estimate, what I'm going to do is I'm going to hit the stat button, and then I'm going to go over to the tests menu. Okay, and then I need to find this 1 proportion z interval, and there's lots of things on here, and we have to be careful. Like here I see 1 proportion, but it's not the interval that says z test, so I keep going. And I think it should be under letter A. If you have a TI calculator, whether it's 83 or 84, 84 plus, or silver, or whatever, I think it's always going to be the same spot. So here's this 1 proportion z int, right? That stands for 1 proportion z interval. And I hit enter there. And it's going to prompt me for the x. And since I checked my assumptions, I know exactly what my x is. It's 125. And the n, right? Again, when I checked my assumptions, I noted that the n was 500. Okay. And the C level stands for confidence level. That's where I enter what my confidence level is as a decimal. And they said that I wanted to find a 90% confidence interval. Okay, so I'm going to use C level equals 0.90. Okay. You just hit 0.9, 0.9, it's all the same. Then I go down and I hit enter on this calculate button. And what it does is it gives me this interval. And it gives me a little bit extra. It tells me the sample size n, but I already told it n, so that's not really helpful. But it also tells me the p hat. This says in this case it's 0.25 or 25%. Okay, what that means is that in our sample, right, we had these 125 mothers. 125 is 25% of our sample, of the 500. Okay, but what we're going to do is we're going to write down this interval, 0.21815. to 0.28185. Okay. And in our notes here that this is what the input screen looks like and what the output screen should look like, okay, for reference. Okay. But we want to write down what that confidence interval is. Okay. On your calculator, I don't see the C level, I just see prop. Let's see. Okay. Does your output look like this? Prop Z, yeah. So what you did is, I think that you picked the wrong thing from your menu. This is the one prop Z test. What we want to do is hit stat, tests, and go all the way down to the one prop Z int. It stands for interval. So make sure you hit that one. Otherwise, your input and output is going to look different, and it's not going to give you what you want. Okay. All right. So that's the input and the output that we should get. All right. This does not answer our question. What we want to end up with is not just a bunch of crazy numbers. We want to be able to say something in words to answer our question. Okay. So, and that's this last step here. We want to give a conclusion in context, right? You don't need to be creative. You're learning this stuff now. So when we write a conclusion, you don't have to come up with some creative understanding for what's going on here. We can sort of mimic this same statement every time. And I'm not saying that that's sort of ideal, but for the learning process, I'm trying to keep things simple. Okay, so we are C% confident. So in our example, we could say 90% confident that proportion of all, in this case, object of the same category. So we'll write that in the context that we're talking about with these new mothers, is between, and then we give our lower endpoint of the interval and the other upper endpoint of the interval. Okay. So let's write our. So this was our name the test, and this was the I step, create a confidence interval. So now let's do the conclusion. Okay. We created a 90% confidence interval, so we can say we are 90% confident that the percentage of all mothers in Tajikistan that breastfeed is between. And what I'm going to do is I'm going to look at the numbers that I have here and just convert it to a percentage. So 0.21815, if I move the decimal twice, is 21.815%. Okay, and that's where I'm getting these percentages. I just moved the decimal over. Okay, so this is in words what this confidence interval means. We're 90% confident that the percentage of all mothers in Tajikistan that breastfeed is between 21.815% and 28.185%. Okay. Now, the reason that I capitalized all here is because when we're writing our conclusion for a confidence interval, we're not talking about the sample of 500 mothers. Okay? I don't need to know anything about confidence intervals or interval estimates. Okay? I can say that in that sample of 500, it was exactly 25% of mothers who breastfeed. End of story. I don't need any sort of guesswork, confidence intervals. I don't need anything more complicated than what we did in our first couple of sections of stats. Okay? What we're doing here is we're using that interval to tell us about the whole population. We're saying that sample of 500 is going to inform us about the whole country, but we know that the whole country might differ a little bit. So we're only 95% confident that that sample is accurate. And the accuracy is limited to saying that the percentage is somewhere in this range. Okay. Here's another way to look at that. Instead of saying that it's between 21.815% and 28.185%, there's another way that we can look at that. Okay. If I look at this interval, right in the middle is going to be 25%. Okay, you could see that because it tells you the p-hat, or you could also just average those two numbers, right? If I take 21.815 and 28.185 and average them, right? Add them and divide by 2, I get exactly 25. So 25 is in the dead center. Okay, so if I take 28.185 and I subtract 25, I get a distance of, we'll just round that. We'll say that that's about 3.2. Okay, so what we'll do is we'll say, all right, this distance here is about 3.2%. And the same thing on the other side, right? The other side, the distance is 3.2%. Okay, that measures our margin of error. Okay, so another way that we could write our conclusion, instead of saying that our percentage is in between these two numbers, what we could do is we could say that it is 25% with this margin of error. Okay, so another conclusion that we could give, we are 90% confident that the percentage of all mothers in Tajikistan that breastfeed their infants is 25% with a margin of error of 3.2%. And that's probably a little bit more like the format that you're likely to consume, you know, when you look at news and stuff like that, okay, or look at articles online. They typically give you the point estimate, and sometimes they'll give you the margin of error. Oftentimes that margin of error will be buried in a footnote. I never see the confidence level. That's almost never reported. Most of the time, though, in most disciplines, that's supposed to be 95%, like across the board. So like when you're doing sociology and economics and things like that, that's kind of just the standard that they go by, and they don't, you know, typically deviate from that. When you're doing things like physics or medical research or things like that, then those confidence intervals often change because they need certain levels of precision to make decisions. Okay, so it certainly can change in certain contexts. It's in most contexts going to just always be 95%. And when outside of like a scientific study, if you're just reading an article, they almost never tell that to you, right? They don't tell you the level of confidence. Okay, which is terrible, but you know, it's to keep the confusion down. When you put a bunch of percentages in the same sentence, now everyone's confused, right? So we have to be careful. All right, this is the process of using a sample to tell us about the population, okay, via a confidence interval. All right, so we'll call that quits for today.